Okay, for the practice 2 problems, I want you to try 1, 2, and 3 here, and we're actually going to get rid of question 4. So I want you to try these on your own first, and then we'll you can pause the video and then we'll go through them. So for practice 2 problem 1 here, it says what is the KSP expression for NaCl turns into Na plus and Cl minus? Now we could start out here and say KSP equals the concentration of Na plus times Cl minus, but technically we don't have an equilibrium here. So think about why we don't have an equilibrium here. I guess it kind of has to do with the fact that sodium chloride is a soluble salt. So pretty much all of it's going to dissolve. So we really don't do KSP problems for things that are soluble. And we also kind of see that there's no equilibrium here by the fact that there's this single-sided arrow. So for this little kind of trick problem, I really wouldn't set this up because NaCl is soluble, which means we're not really going to do KSP problems. We only do KSP problems for things that are like only slightly soluble or insoluble, mainly insoluble. Okay, let's check out question 2. So this bismuth sulfide compound, Bi2S3, has a solubility of 1 times 10 to the negative 15th at 25 degrees Celsius. Calculate KSP. So again, I think we should always start out by writing down the chemical in the solid form and then looking at the dissociation or the dissolving reaction, the dissolving equilibrium. It looks like we have 2 bismuth ions. If this is Bi2S3, it means the bismuth probably has a charge of +3, and there's 2 of them. And remembering from the periodic table, sulfur was 2 away from the noble gases. Sulfur is always a -2, and there would be 3 sulfurs. So these subscripts usually become these coefficients. Okay, now that I have this set up, I can set up my KSP expression. For this reaction, it would be the concentration of bismuth squared times the concentration of sulfur cubed. Okay, now this one's a little weird in that the KSP will equal these solubility values. Now, if it says Bi2S3 has a solubility of 1 times 10 to the negative 15th, what's the ratio between bismuth sulfide and bismuth ions? It's a 1 to 2 ratio. So if this was 1 times 10 to the negative 15th, this would be 2 times 10 to the negative 15th. Again, because it's a 1 to 2 ratio. And if this was 2 times 10 to the negative 15th, what would the concentration of S minus 2? So again, this is a 1 to 3 ratio. So this would be 3 times 10 to the negative 15th. Okay, so now that we have this set up, we can plug in the values. And we could do 2e minus 15. Oh, and this would have to be squared times 3e minus 15 to the third. And we get 1.1 times 10 to the negative 73. What does this huge negative exponent mean? It means this bismuth sulfide thing is very, very, very unsoluble. And this tiny little number means barely any of it will dissolve, but a tiny bit does dissolve. Okay, the last problem here, I don't know why it's 5. Problem 3. Calculate the solubility. That means we're solving for X of calcium sulfate if the KSP is 7.1 times 10 to the negative 5th. Calcium sulfate, calcium is a +2. Sulfate's a -2. Sulfate is SO4. This would be a solid. That means I get Ca +2 and SO4 -2. Now notice that it's important to get this formula right because now we see there is a 1 to 1 to 1 ratio. Okay, now the KSP expression should be what we set up next. KSP would equal the concentration of calcium raised to the first power times the concentration of sulfate ions raised to the first power also, because this is a 1-to-1 ratio. And then it gives us KSP here. So KSP is 7.1 times 10 to the negative fifth. And here's where we're going to set up X values to represent solubility. And the X values will just be these mole ratios raised to a certain power. So since I have a mole ratio of 1 here, I'm going to put in 1x, and then I'm going to raise that to the first power because it's a 1. Again, for sulfur, the sulfate is also a 1 here, so I'm going to put 1x, and I'm going to raise that to the first power again because there's one of them here. So for this problem, the KSP value just equals x squared. 7.1 times 10 to the negative fifth equals x squared. So we can just do the square root of 7.1 times 10 to the negative fifth. And the solubility this time, x equals 8.4 times 10 to the negative third. And we're calculating for solubility, we should get the molarity unit down. Okay, I'd like you to skip question 4. We're not doing these types of problems this unit. And this would be our expectation.